Welcome back to another video for 8th grade math. I know that you guys love these videos. That's why I'm cranking them up every day. Or more like you have to watch them anyway. But, I appreciate the support. 14 subscribers last time I checked. From 0 to 14. I'm going to get to 1 million like this anyway. And so today we're going to do inverse variation for 8th grade, which is actually not all that hard if you understand direct variation. And so it's something that it has to do a little bit with, but it's not quite the same as direct variation. So let's get into it. And I know that I'm probably going to gain like 1 or 2 more subscribers from this amazing video. All right, so before we even get to the examples, I'm going to go a little bit over direct variation and then inverse variation, which is the new one. This one's the new one. So direct variation, the first thing that you should always remember is that as x goes up, y goes up. And as x goes down, y goes down. Pretty easy, direct variation. And in here, though, it's obviously inverse and direct variation are relation between two variables. And so as x and y go up, as x goes up, y goes up, and as x goes down, y goes down. That's for direct variation. For inverse variation, as x goes up, y goes down. And as x goes down, what do you think is going to happen? Y is going to also not go down, but up. It's going to go up. And so that's the main difference at first, at a glance. And so one of the things that you have to understand about direct variation is that the graph crosses the origin, right? The origin. So graph crosses origin. Which is 0, 0, and it's a straight line. Right? Graph crosses the origin, and it's a straight line. And here, the graph doesn't cross the origin, and it's not a straight line. In fact, it's curved. So what do I mean by this? So in here, if we have a small graph, this is going to be the graph for direct variation. This little thing, y, x, and then the little line. And in here, it's going to look something different. We're going to have the y, the x, and it's going to go like this. It's never going to touch x. So my hand just got too excited, I guess. This is it. So it's actually never going to touch y. It's never going to touch x. And it's going to look like a little curve like that. And that's what it is. I erased the origin. So that's some of the main difference, right? Let's look at other difference in between direct variation and inverse variation. Another difference is that the formula here, it's going to be y equals kx. And to find k, which is a constant of variation, or proportionality, same thing. I'm going to call it variation, but it's the same thing as the constant of proportionality. The important part is that you understand that k is a constant and x and y are both variables. So to find k, what you're going to do is you're going to divide y by x. And that's how you find it. How did I do that? I divided x over here and it ended up here. So k equals y over x. That's another important thing about direct variation. Now in inverse variation, the formula is going to look like this. Y equals k over x. Okay, that's the formula for direct variation. This is the for inverse variation, my bad. This is direct variation, y equals kx. Inverse variation is y equals kx. This, again, is the constant of proportionality, I'm going to call it here, but it's the same thing. All right. And how do we find k? Well, very easy. To be able to get k by itself, because x is dividing the k, we're going to multiply x on both sides. And so to find the k, we find that k is going to be y times x. And that's how you find k for inverse variation, and for direct variation is k equals yx. So today we're only talking about this part. You have to keep in mind y equals k over x, where k is a constant of proportionality, and to find k we have to multiply the y and the x so that we find what that is. Now let's get into the examples. All right, so example 1, it says that Trin is actually traveling at 60 miles per hour and to go visit his friend, and then it's going to take him 2 hours if it drives at 60 miles per hour. And so the first question is, what remains constant here? Well, rate is going to be miles per hour, meaning the speed he's going, and the time, obviously, it's the amount in hours. So to be able to find that out, we need to find, okay, is this inversely proportional? And let's think about it. Is there something that remains constant? Well, if Trin started at his house and he's going to go to his friend's house, it's not like his house and his friend's house are going to just suddenly switch places or move closer, move further away. So what is constant in here is the distance. Now, do we know the distance here? No, we don't. So to actually find the distance, what we're going to do is we're going to multiply these two, because if he went 60 miles per 1 hour, then in 2 hours, how far did he go? So if 60 miles is 1 hour, then in 2 hours it's going to be 120 miles. So 120 miles. That's the answer for A. All right. A means, okay, so what's constant here is 120 miles. That's going to be our constant of proportionality. Now look at what happens. The slower he drives, what do you think? He's going to get he's going to get there quicker if he starts driving slower to get to his friend's house? No, it's actually going to take longer. How come? Because if we set it up like an inverse variation, and we said that 120 is k, then we're going to say, okay, y is the amount of hours, like how many hours it takes, and x is going to be my rate, how fast he's going. So how many hours is it going to be if he drives at 40 miles per hour? Well, the zeros cross out, and 12 divided by 4 is 3. So y would be 3 hours. Well, it takes him 3 hours. So the slower he drives, the more it takes. So as the rate goes higher, the time will go lower. But as the rate goes lower, the time will go higher. It will take him more hours. So let's do the next one with 30. I don't have to erase the whole thing. So y equals then 120 divided by 30. Okay, so the zeros cancel out, and 12 divided by 3, y equals 4. It takes him 4 hours if he drives twice as slow. 30 miles per hour is going to take 4 hours. And then finally with 20, look at that. I don't even have to erase the whole thing. I'm just going to erase the 12 divided by 2. It's 6 hours. So he could get there in 6 hours. It's probably better that he goes running or something, you know. He would enjoy it more than going at 20 miles an hour and getting there at 6 hours. So that is going to be B. B, we completed the table. And then C says, is this a proportional, inversely proportional, right? Yes, it is inversely proportional because as the rate went higher, this went lower. But as this started to go lower, this started to go higher. This started to go lower. This became even higher. This became even lower. This became even higher. And this is why it's inversely proportional, because if the rate of speed goes higher, the time goes lower. But if it starts to drop down, the rate of speed, then the time would actually increase. And that's why this is a inversely proportional relationship. All right, so in the second example, which is the last example, I know, long lesson, right? I was getting tired too. So what happens here is that we're going to talk about these robots that make this widgets. A widget is whatchamacallit, or a thingamajig, or something like that, you know? So I like to clear things up for people, and I think I did with the widget thing. So obviously now everybody knows what a widget is. If not, you can just, go back a little bit where I literally just explained it. And I love that about videos. I don't have to repeat myself. You can actually just go back, and then I don't have to repeat myself. Because somebody's going to be like, can I go to the bathroom? When I said I was explaining something, and then, the whole thing, he might not even go to the bathroom then. And so hopefully you can pause and go to the bathroom. If not, then you can just wait until this beautiful video is over, and then you can go. Same thing with water, or snacks, or anything really. So now that we actually have this there, we're going to find out how long does it take 20 robots to do it. Now, if it took 10 robots to do a fixed amount of widgets, or whatchamacallits, or thingamajigs, or husumatsits, or whatever it is, then how many hours would it take 20 robots? Well, the thing is that it doesn't make sense that 20 robots would work for more hours than 10 robots. So we know that as the number of robots increases, the hours decrease. But we need to find out what is K. How many widgets did they make? So to find K, I told you that you had to multiply Y times X. The same thing as X times Y. It's literally the same thing. So K would be the same thing as 8 times 10, which is super hard math right here. Try to fight the temptation of using a calculator, all right, or your phone, or whatever it may be, but it's 80, right? Because 8 times 10 is 80. Wow, crazy. And so K is going to be 80, and then what we're going to do is we're going to find the hours. Again, the hours are going to be Y. Why? Because it is, okay? And so K is going to be 80, which we just put right here. And then X is going to be the amount of robots, which is 20. Look at that. We cancel the zeros out because 10 divided by 10 is going to be 1. And so 8 times 1 is 8. And 2 times 1 is 2. Crazy math right there. And then 8 divided by 2 is going to be 4. Look at that. It took them 4 hours to finish the widgets, the whatchamacallits, or whatever it is that you want to say it is. And so that's it. This is lesson 99, I think. And then tomorrow we have lesson 100. So we've done 100 lessons in the book. That means there's only 20 to go after tomorrow's lesson. So I know some of you are excited. Thank you to everyone that watched the video, to all my likers, commenters, subscribers. And if you like this video, consider subscribing and consider watching the other lessons. Maybe even the 7th grade lessons, You might enjoy them. If you like math, I don't know. But I will see you in the next one. All right. Peace.